Hi, I'm Dr. Michael Maedo, PhD by Texas A&M University and teaching a research assistant at São Paulo State University. Today, I will talk about modeling the heat and fluid mass transfer in induced fractures in deformable geo-reservoirs using high aspect ratio interface element. And why is this topic so important? Well, because the extraction of natural resources from geo-reservoirs requires advanced techniques to increase the productivity of the reservoir and at the same time prevent environmental problems. One example of such technique consists of injecting a fluid at a very high pressure to induce the creation of fractures and therefore enhance the permeability of the reservoir. This technique is called hydraulic fracturing, and its study requires a coupled thermo-hydromechanical formulation because the difference between the temperature and the pressure of the injected fluid is significant. The finite element program, CodeBright, was designed to deal with the heat transfer and fluid mass transfer in deformed porous media by considering the continuum mechanics concepts. But the program is not capable of predicting the behavior of porous media with discontinuities. And discontinuities in the forms of fractures or cracks are very common engineering problems, especially in the case of fractured geo-reservoirs, which the hydrothermal fracturing process controls the behavior of the system. Therefore, in this work, high aspect ratio interface elements, finite elements, equipped with a tensile damage model, will be used to tackle the thermo-hydromechanical behavior of fractures. Such elements are inserted between the regular 3-node triangular elements of the mesh in the case of 2D problems during the pre-process stage, fragmenting the mesh. The same occurs with the 3D. In the case of triangular elements, we're going to use tetrahedral elements. This is the reason why this technique is called mesh fragmentation technique. To show an example of the effectiveness of the MFT, mesh fragmentation technique, let us assume a reservoir with a borehole at its center, in which the in-situ temperature is 70 degrees Celsius, the in-situ pressure is 10 megapascal, and the vertical and horizontal stress field of the reservoirs are 20 megapascal and 25 megapascal respectively. A 20 degrees Celsius fluid is injected at a rate of 0.01 kilograms per second. As a result, we can see the evolution of temperature, pressure, and fracture propagation throughout 10 hours of injection. It is important to observe that the secondary cracks formed due to the thermal retraction induced by thermal gradients. Well, this is a very simple example, shows that the mesh fragmentation technique is a very promising technique to simulate this type of problem, and we will continue investigating the thermal hydromechanical processes in geo-reservoirs by using such technique. And finally, I would like to thank the financial support provided by ANP and also CNPq. Thank you all for watching this video.